In this module, Module 2, we're going to talk about number systems and converting between number systems. So we'll talk about decimal numbers, binary numbers, hexadecimal numbers, as well as other number systems. And then we'll also talk about signed numbers, both signed magnitude and 2's complement numbers. Although in the course, we'll mostly deal with 2's complement numbers, as well as binary and hexadecimal numbers. Throughout our discussion of the number systems, we'll also talk about how to convert between each of these number systems as well. So before we dive into the details of these number systems, let's take a step back and look at the history of really dealing with binary variables. George Boole, who was born in 1815, really laid the groundwork for interacting with binary variables and what we'll talk about in Chapter 2, which is Boolean algebra, so manipulating these variables as well. He was born to working class parents, and he taught himself math and joined the faculty of Queen's College in Ireland. So the work that describes his discoveries with binary variables and Boolean algebra is called An Investigation of the Laws of Thought. So in Chapter 2, we'll talk a little bit more about how we interact with these operations and, or, and not. But for now, let's focus on binary variables and, in general, number systems. So we'll first talk about decimal numbers because we're all familiar with that. And then we'll talk about binary numbers, which is base 2. Binary is bi being base 2. And then we'll talk about hexadecimal numbers, which are base 16. So let's first review our decimal numbers. So here we have our everyday base 10 number system. So deci, we have our base is our base 10 number system. This is our everyday number system. So if we look at the digits of this, we'll have our ones place, our tens place, our hundreds place, thousands place, and we could keep going as well. ... So we think of this as the ones place, the tens place, the hundreds place, the thousands place, etc. And really, this is the 10 to the 0. So here's our base 10 raised to the power of 0. The next digit has the value of 10 raised to the power of 1. So that's the tens place, but again, we just have our base raised to the next number, 1. The next place is 10 raised to the second power, or 100. And finally, we have 10 to the 3. And we could keep going, 10 to the 4's place, 10 to the 5, 10 to the 6, and so forth. So each of the digits has a place value, so the ones column, the tens column, the hundreds column, the thousands column, etc. And then we have an actual value there. So in this case, we have the value 5, 3, 7, 4. So if we wanted to figure out what value this was, we would take that digit and multiply it by the column value. So 4 times, well, what's 10 to the 0? Anything raised to the 0 power is 1. So 4 times 10 to the 0th power, or just, that value is just 1. And then we add it to the next digit times its column value. So 7 times, well, this one is 10 to the 1, or the tens place. So that's just the 7 times 10, plus our next digit, 3, times its column value, which is 10 to the 2, or just 100, plus our final digit, which is 5 times 10 to the 3, which that's just 1,000. And so when we add these all together, we get our value 5 times 1,000 plus 3 times 100 plus 7 times 10 plus 4 times 1. We get 5,374. We'll follow the exact same process when we use base 2 numbers or binary numbers, but instead we have a different base 2, but the process is exactly the same. So if we look at our digits, now they're binary digits or bits. We have our base 2 to the 0th power. Next binary digit or bit is the 2 to the 1st power. The next binary digit or bit has the weight of 2 to the 2nd power. Next column is the 2 to the 3rd power, ... 2 to the 4th, 2 to the 5th, 2 to the 6th, and so on. And now we can say what these are. Well, 2 to the 0th power, anything to the 0th power again is 1. 2 to the 1st power, 2. 2 to the 2nd power, 4. 2 to the 3rd power, 8, and so on. 16, 32, etc. And so here, that's what we have written here. The 1's column, the 2's column, the 4's column, and the 8's column. And now with binary numbers, it's kind of easier because we just have 2 possible values, 1 or 0. So that column is either there or not. So in this case, the number we have to the left is 1101 in base 2 or binary representation. And so if we want to figure out this value, we're going to take the bit or binary digit and multiply it by the column weight. So in this case, 1 times 2 to the 0 plus, well, the next one we don't have, 0 times 2 to the 1, or 2, plus, next one, 1 times that column weight, which is 2 to the 2, or 4, plus our final value, 1 times that column weight, 2 to the 3. So again, either the column weight exists in our equation, or in the 0 case, it doesn't. So we could write this again as, well, 1 times 2 to the 3 is just 8. 2 to the 3 is 8, plus 1 times 2 to the 2, which is 4, plus 0, plus 1 times 2 to the 0, which is just 1. And we end up with the value 13. And so here we have it written out or typed out as well. So again, when we see a binary number, we can say, well, is that column present? Or, in this case, not present. And we could say, well, let's see, there's a 1 column present plus a 1 in the 4's column plus a 1 in the 8's column. And we get our value 8 plus 4, 12 plus 1, 13, base 10. And we can put that subscript to let us know what base we're dealing with. So this is 13 base 10. And again, here we have this base 2 indicating that that's not 1101 base 10, is in fact 1101 base 2. So one thing you'll notice when we're dealing with binary numbers is these powers of 2 are really important for us to understand and really be able to recall pretty quickly. So knowing these powers of 2 is one thing you want to start with getting familiar with and just practicing. So 2 to the 0, 1, 2 to the 1, 2, 2 to the 2, 4, 2 to the 3, 8, 2 to the 4, 16, 2 to the 5, 32, 64, 128, 256, 512, 1024, and really that's kind of all you need to know. Up to 2 to the 10, 2 to the 9 is a good place to know. You know, the rest is kind of trivia, 2048, 4096, blah, blah, blah. But really handy to be able to recall and memorize up to the power 2 to the 9th. So let's do some examples of binary to decimal conversion. So here is a binary number, again indicated by this base 2, or you might just say this binary number 10011 also indicates that it's a binary number. Now we can just say, okay, well, the way we're going to convert this to a decimal number is let's figure out which columns are populated with ones. Well, the ones column has a 1 in it, as well as the twos column. The 4s and 8s column have zeros in it, so those won't be in our addition. And finally, the 16s column also has a 1 in it. So we add those together. Well, 1 times 16, which is 16, plus 1 times 2, which is 2, plus 1 times 1, which is 1, and we get the value 19 base 10. So this is the process for binary to decimal conversion. We can also convert from decimal to binary. There are really two methods. The first method is the recommended method, but I'll show both methods just so you can have some redundancy, and we'll use the second method for some other bases. All right, so the first method is to find the largest power of 2 that fits into a decimal number, subtract it from that decimal number, and repeat. Method 2 is to repeatedly divide a decimal number by 2 and put the remainder in the next most significant bit. Okay, so let's focus first on method 1, finding the largest power of 2 that fits in the decimal number. So here's method 1. We have some decimal number, 53 base 10, and we can think back to a couple slides ago about the powers of 2. So we have 1, 2, 4, 8, 16, 32, 64. Okay, so 64 was too big, but 32 would fit in 53. And what you'll want to do is write out those places or those column values as you go. So we have the 1, 2, 4, 8, 16, 32. So we have the 1s column, 2s column, 4s column, 8s column, 16s column, 32s column. We're not going to have a 1 in the 64 column, 64s column, because that would make it too big. If you had a 1 there, now it's a number that's 64 or larger. So 32 is the highest value that we need to go to, and we'll put a 1 in that place. So by having a 1 in 32's place, we know that this value is 32 or larger. So now we can say, well, okay, we've got 32 taken care of. 53 minus 32. Now we have 21 left that we still need to account for. The next largest power of 2 that fits is 16. So we put a 1 in the 16's place. And again, we subtract 5. Now, the next largest power of 2, well, 8 doesn't fit. 8's too big. But 4 fits. So we'll put a 1 in the 4's place, or the 4's column. And now we have 1 left. And so 2, too big. But we can put a 1 in the 1's column. Subtract that, and we get 0. So now we just fill in with zeros for the rest of the places, that the binary representation of 53 is in fact 110101. And written out, here we have a typed out version of what we just did. Okay, so let's now talk about the second method. Again, this first method is the recommended method for conversion from decimal to binary. But let's talk about the second method as well, just for redundancy. And again, we'll use this second method for other bases, not base 2. So for this method, we're going to repeatedly divide by the base, in this case base 2, and the remainder will go in the next significant bit. So let's start by looking at decimal. So let's say we have the number, we'll use the same number, 53. We could find the places, the values of each column by dividing this by its base 10, Well, 53 divided by 10 is 5 with a remainder of 3. And this remainder, that 3, is what we'll want to put in the next significant bit. Well, we're starting at the least significant bit, which is 3, is the ones column. So that 3 goes in the ones column. And then we take our 5 and divide it again by 10. And we get 0, remainder 5. And so now that's what goes in the tens column. And so it seems kind of silly because, 53, we get 53 back. But this process is the same process we're going to use for any other base, including base 2 or binary numbers. So let's think about it. 53 divided by 10, this first process. Well, if I divide it by 10, basically anything that's the remainder doesn't fit in the tens column or higher. And so that's going to have to go in the ones column. So this 5, I've already divided it by 10. So dividing by 10 again really is dividing 53 by 100. So anything that's left doesn't fit in the hundreds column or higher. So it has to be put in the tens column. Okay, so the process again is to repeatedly divide by the base, in this case base 10, and put the remainder in the next most significant digit. So now let's do this with base 2. So we'll use that same number, kind of a random number here, but 53. And we'll repeatedly divide it now by the new base, which is 2. So 53 divided by 2 is going to give us 26, remainder 1. So that 1 goes in the least significant bit. And then we take what's left, the 26 here, and divide that again by the base. Divided by 2. We're going to get 13. Remainder is 0. That goes in the next most significant bit. And we take what's left, the 13, divide that by 2, and get 6. Now we have a remainder 1. It goes in the next most significant bit. Again, same process, take what's left, 6, divided by 2. We're going to get 3, remainder 0. That remainder goes in our next most significant bit. And then we go to take that 3, divide it by 2. We're going to get 1, remainder 1. 1 goes in that remainder goes in our next most significant bit. And then we take what's left, our 1, divide it by 2, and we get 0, remainder of 1. And that's what goes in our next most significant bit. And as expected, we get the same value as we got with method 1. If not, there's probably an error in there. So why is method 1 recommended over method 2? Well, addition's a lot easier for us to do than division. Method 2, it's easy to make mistakes. Easier to make mistakes in method 2 than method 1. But again, they both give us the same result. The first method, as you saw, was pretty fast and less prone to errors. So again, method 1 is the recommended method, but they both work. And again, typed out the same process that we just did on the prior slide. All right, so let's do some examples here. Binary to decimal conversion. We're going to take some binary number and convert it to decimal. Well, same process that we did before. There's a 1 in the ones place. We put a 1 plus. There's a 1 in the, not in the 2s, but in the 4s place. So we add a 4. There's a 1 in the 8's place. We got an 8. And finally, there's a 1 in the 16's place. So we add a 16, and we get 16 plus 8 plus 4 plus 1. We get 29 base 10. And we can also do decimal to binary conversion. First, we get the largest power of 2 that fits in the value 47. 1, 2, 4, 8, 16, 32, 64 is too big. So again, recommend writing down these column values, the 1's place, 2's place, 4's place, 8's place, 16's place, 32's place. Again, remember the 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5's place. And we put a 1 in the largest power of 2 that still fits in 47. So we don't go up to 64, the 64's place here, because that would be too big. But we put a 1 in the largest power of 2 that fits. So we have 32 taken care of. What do we have left? We have 15. So 16 is too big, it doesn't fit, but 8 does. So we put a 1 in the 8's place. And we have 7 left. And so now we see that 4 fits. So we'll put a 1 in the 4's place. We have 3 left. 2 fits. So we'll put a 1 in the 2's place. And we end up with our last number, 1. And so we put a 1 in the 1's place until we finally get down to 0, and we're done. Fill in the blank places with zeros, and we have our binary representation of 47 base 10. And here we have both of those processes typed out for you as well. Okay, so let's take a step back and think about the ranges and values of these different numbers, both base 10 decimal numbers and base 2 binary numbers. So we can think about the values, so what values can I represent, and the range, or what's the smallest number I can represent and the largest number. So with an n-digit decimal number, whenever you come across a problem with a variable, so n-digit, that n could be 1, 2, 3, 5, 48. First, do a simple example. Not so simple that it's trivial, like 1, but reasonably simple that you can do it by hand. So let's do an example for a 3-digit decimal number. So for a 3-digit decimal number, we have 3 places. Well, first of all, how many possible values can we represent? And what is the range? So let's start with the range. Well, the smallest value is if we put all zeros in that 3-digit value. Okay, that's the smallest one. And the largest value we can represent is if we put the largest digit in each of those places. So the range of our 3-digit decimal number is 0 to 999. And how many different values could we represent? Well, 1 to 999 is 999 values, but we can also represent 0. So the number of values, how many values, the number of values is 1,000, or 10 to the 3. With a 3-digit decimal number, we can represent 10 to the 3 different values, or 1,000 different values, 0 to 999. And the range is, if you want to write it in terms of this 3-digit decimal number, the range is 0 to 10 to the 3, well, it's not 1,000, it's close, 10 to the 3 minus 1. And now that we've done it for a specific n, so n equals 3 in this example, our example is for n equals 3, a 3-digit decimal number. Now we can extrapolate and say what it would be for an n-digit decimal number where n is any value, any integer. So how many values can we represent? Well, with n we can represent 10 to the n different values. And the range is, well, the smallest value is always going to be 0 to 10 to the n minus 1. And so we can do the same thing with binary numbers. So we can first look at an example. Again, some reasonably simple example, but not trivial. So trivial would be a 1-bit binary number, and reasonably simple is 3 instead of 5,000. Okay, so let's do the same thing we did before with our decimal numbers. The range is, well, let's see, we have a 3-digit binary number, or a 3-bit number. And we want to look at the smallest value we can represent and the largest value. Well, the smallest value is clearly 0, 0, if we put zeros in each of those bits. So we have the value 0 to 1, 1, 1 is the largest value. We put the maximum value in each of the bits. And 1, 1, 1 is, well, 1 plus 2 plus 4. Remember those place values, or the column weights. The 1's place, the 2's place, and the 4's place. So we have 1 plus 2 plus 4, we get 7. So our range is 0 to 7. And the number of values we can represent is, well, let's see, 1 to 7 is 7 different values plus 0. So the number of values is 8. And if we think of what we did in the decimal number analysis, we can think, okay, well, let's see. 8 is a power of 2, 2 to the 3, in fact. And this range is 0 to 2 to the 3 minus 1. So now we can extrapolate that example and say, okay, well, how many values can we represent? 2 to the, for an n-bit binary number, 2 to the n. For a 3-bit binary number, it's 2 to the 3. So for any n, it would be 2 to the n. And the range is 0, smallest number, to the largest number, 2 to the n minus 1. So we did two things. We looked at a number system that we're very familiar with, decimal number systems, to help us understand binary numbers. And we used a relatively simple example to help us understand the ranges. So while you can memorize these ranges, it's always good to be able to fall back on doing a simple example to verify that you didn't forget to write the minus 1, you didn't put the minus 1 up in the exponent, you didn't do any number of possible errors there. You can do a quick example to verify that the equation that you wrote was correct. Okay, so here we have written out nicely what we just figured out from the prior slide. So the number of values we can represent for an n-bit decimal number and the range of that n-bit decimal number, as well as the same values, the number of values you can represent and the range for an n-bit binary number. So now we can basically take what we've been doing and write it in mathematical form. And what happens when we see this equation is maybe like, oh, I have no idea what that's saying. We've actually been using this equation for the last few slides that we've been talking about binary numbers. So this is saying that some value A represented by a sub 0, a sub 1, dot, 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 to a sub n minus 1, where n is the number of bits. So again, we'll use an example to make this more concrete. Let's say we have a 3-bit number, or I guess because our example here is 4-bit, let's go ahead and use 4-bit. So a 4-bit number, 4, we'd have 4 places in our number. This is the a sub 0 value, a sub 1, a sub 2, and a sub 3. So it goes to a sub n minus 1. In our case, n is 4, so a sub n minus 1 is a sub 3. And then we could put any value in there. We could put the value 1, 0, 0, 1, for example. So a sub 0 is 1, a sub 1 is 0, a sub 2 is 0, and a sub 3 is 1. And so now we get the value A is the value of this number by summing each of the bits multiplied by its column weight from 0 to n minus 1. So let's go ahead and do this for our example. So we start with I equals 0. So we start with the 0 column, take the value, a sub 0 in this case, multiply it by its column weight, 2 to the 0. And we're going to get, well, 1 times 2 to the 0, which we know is 1. And then the summation says, well, now we're going to sum from I equals 0 to n minus 1. Now we'll take the next I equals 1, the next I value, add it to what we just had. So a sub 1 is 0 times 2 to the I, which we're at I equals 1, so 2 to the 1. Sum it, or add it to the next value in our summation, I equals 2. So a sub 2, in this case is 0, times 2 to the 2, 4. And finally we add it to our last I in the summation, I equals 3. So we're going to n minus 1. So n is 4, n minus 1 is 3, a sub 3 is 1, times 2 to the 3. And we get our value. So just like we've been doing before, we get 8 plus, well, 2 zeros plus 1. So in this case, we get our value A is equal to 9. So this binary representation of our value, 1, 0, 0, 1, in binary is equal to decimal 9. And here's another example just below of a different number, 1101. Again, 4-bit, but n could be any number, but n in this case is 4. So we add a sub 0 times 2 to the 0 plus a sub 1 times 2 to the 1 plus a sub 2 times 2 to the 2 plus a sub 3 times 2 to the 3. To get our value, in this case, we have 8 plus 4 plus 1, and we get decimal 13. And you could put that base 10 if you wanted to. Okay, so now we have in mathematical form what we've been doing kind of empirically before this.